Deep in the heart of the Phoenix cluster lies a cosmic monster, a black hole with more than 100 billion times the mass of the Sun. How could something so massive even exist? Tonight, we'll explore the mystery behind the largest known black hole in the universe. If you enjoy these cosmic stories, please like, subscribe and share, and tell us in the comments, what do you think could have created such an unimaginable giant? Thank you for watching. Now let's begin. The Phoenix cluster stands as a very distant and very massive assembly of galaxies in the observable universe, and this region is treated here as the outermost layer before any narrower scales are considered. The cluster environment is defined by gravity acting across very large distances, shaping the locations of its member galaxies and the very diffuse gas between them. A cluster is a bound structure of galaxies that move in a shared gravitational well, and the Phoenix cluster is an example that contains very many galaxies spread across a region measured in many millions of light years. Light from this cluster has taken very many billions of years to arrive at Earth, which means the view is not of the present, but of a much earlier time in cosmic history. The cluster is not a simple static object, and it is not smooth and symmetrical on every level, but it has enough gravitational mass to hold galaxies, plasma and dark matter together as one very large system. Dark matter is a form of mass that does not emit or absorb light, and is inferred through its effect on visible matter and on the motions of galaxies as a group. The Phoenix cluster contains dark matter in a gravitational volume so large that the combined mass of dark matter and normal matter supports temperatures and pressures in a plasma that is far hotter than the surfaces of most stars. The cluster environment can be described as dominated by the three key matter components of normal stars and galaxies: hot gas between those galaxies called intracluster medium, and dark matter, which holds all of this in place through gravity. On the cluster scale, the many galaxies are not particularly dense when compared to the densities found inside galaxies themselves. The distances between galaxy centers are quite large, and the members move in orbits influenced mainly by the overall shared gravitational potential. The intracluster medium is so thin that a cubic centimeter would usually contain far fewer atoms than an excellent laboratory vacuum on Earth. Yet the total mass of this plasma is enormous because the volume is enormous. These gases are heated to many tens of millions of degrees Celsius, a condition created partly by gravity, which compresses the gas, and partly by energy injection from galaxies that emit jets or winds. The temperature of this gas is so high that it emits X-ray light, and this is how astronomers can map some features of the cluster volume. Radio maps can reveal cavities or ripples in this gas when energy from particular galaxies disturbs it. The Phoenix cluster has been noted for several noteworthy features, including extremely luminous X-ray output from its gas and extremely fast cooling rates in some parts compared to many other clusters. But at the level of this first outer region, the focus is only that this is a gravitationally bound system of galaxies, gas, dark matter, and extremely hot plasma. The cluster scale is introduced first because this is the broadest regional frame before narrowing to specific galaxies, and later to one brightest cluster galaxy called Phoenix A, and later still to the nuclear neighborhood of that one galaxy. For this section, only the context is cluster-wide and environment-wide. Light from the cluster arrives after traveling distances so great that the scale of time in this image is measured in billions of years before the present day. It is also important to note that the Phoenix cluster is one cluster among many clusters found through various sky surveys, and its particular properties are discovered through careful study of the faint patterns of X-ray emission and radio features. observers determine positions and brightness distributions from across the electromagnetic spectrum, and each wavelength regime reveals a different detail of the cluster environment. Optical light reveals galaxies, radio structures can show plasma disturbances, and X-rays show the very hot gas in between those galaxies. On the cluster scale, all of these signals combine into physical maps of a region, spanning many millions of light years. But within this cluster, the gravitational field is such that the member galaxies do not disperse into empty space. Rather, they move in orbits inside a shared gravitational well. The velocities of these galaxies are not random but reflect the deep gravitational potential of the cluster mass. Galaxies can interact over long time intervals, and gravitational effects can slowly strip gas or stars from some. In many clusters, the very central galaxy can grow larger than its neighbours, though that feature is not considered here until the narrower region for that one galaxy. Here only the outer shared cluster gravitational context is described. The overall mass is so great that a fraction of the baryonic matter remains in the form of very hot plasma distributed between galaxies. This plasma itself has structure that relates to gravitational gradients and to the energy output of galaxies in the cluster core. But energetic details remain outside the present scale. The present scale is the environment in its broadest form, a frame so large that only cluster-wide conditions are considered. The cluster can be viewed as a gravitational basin filled with galaxies surrounded and permeated by hot plasma that cannot cool quickly in most places because of low density. The location of each galaxy in this giant gravitational field is not fixed permanently, and over cosmic timescales galaxies drift along trajectories influenced by encounters and by frictional effects from the plasma. But this drift is slow compared to luminous events that can occur in the nuclear region of a galaxy, which will not be considered yet. The Phoenix cluster is also distant enough that some fine structure of its member galaxies cannot be resolved. The level of detail available depends on instrument sensitivity and resolution, and certain measurements of the cluster statement are model-based rather than direct. The distance to this object means that astronomers see the cluster as it existed very long ago, and this is relevant to the simple fact that cluster-wide structures are subject to cosmic evolution. In this region, Scale 1 may state only that the cluster exists as a gravitationally bound system with very many galaxies with thermal plasma at extremely high temperature and with enormous mass in both luminous and dark matter. This environment is the container inside which all further inner features exist, but none of those inner features are introduced yet. All further details of particular galaxies, particular emission structures, or particular nuclear activity are reserved for narrower scales. For this first outermost region, the most complete description is simply that the Phoenix cluster is a massive distant cluster of galaxies with a hot intra-cluster medium bound by gravity and visible in part through high-energy emission from the gas that fills the spaces between galaxies, and that this enormous environment is the broad contextual stage in which all narrower structures reside. The intracluster medium is the hot plasma that fills the vast spaces between the galaxies inside the Phoenix cluster, and the present focus remains on this gas as a discrete regional layer, rather than on any individual galaxy within it. Plasma is a state of matter in which electrons are not bound to atomic nuclei, and in clusters this plasma is very tenuous, yet it carries very large total mass because the volume is so large. Even though this plasma is far less dense than most laboratories could maintain on Earth, at the scale of very many millions of light years, this faint material contains substantial energy and is continuously influenced by the shared gravitational potential of the cluster. Temperatures of tens of millions of degrees Celsius in this plasma make it a powerful emitter of X-ray light, and X-ray observations from orbiting telescopes allow astronomers to infer both the temperature and the distribution of this hot material. In many clusters, the plasma cools slowly because density is low, and cooling rates depend on the square of density. But the Phoenix cluster became notable because its intracluster medium contains regions in which cooling happens at unexpectedly high rates compared to many other clusters. Cooling is the process in which thermal energy is lost by emission of radiation. As this gas radiates light, its energy decreases, and the temperature can drop over long cosmic timescales. If cooling happens faster than other energy injection mechanisms can replace the energy, there can be condensations of gas, or changes in the plasma that result in the formation of cooler clumps. These cooler clumps can drift or settle toward regions of deeper gravitational potential, potentially feeding galaxies in the core region, though that inward path is not yet considered here, because the present focus is strictly the cluster-wide plasma environment. The intracluster medium is not still. It is part of a dynamical environment with shocks, ripples, and cavities shaped by previous energy releases from galaxies or from the combined effect of motion of cluster members. In some clusters, supernova galactic winds or jets from nuclear regions can heat gas or inflate bubbles of lower density inside this plasma. These bubbles can move outward buoyant in the hotter surrounding medium and can create structures that remain visible in X-ray and radio maps. But for this section, these structures are not tied to specific galaxies, only cited as general conditions sometimes present in cluster environments. The Phoenix cluster is known for large-scale X-ray brightness and rapid cooling signatures, and the plasma plays a central role in that. The cooling time is a concept which measures how long it takes for gas to radiate its thermal energy under current conditions, and in many parts of the Phoenix cluster, the cooling time is shorter than in numerous other clusters studied across the sky. But even here, these timescales are very long when compared to human timescales, and cooling flows need to be understood in a strictly cosmic context. The term cooling flow refers to the slow inward drift of plasma toward deeper gravitational wells when cooling outpaces heating, and this can cause material to eventually reach a central baryon reservoir. However, this step is not yet the present focus. The essential point for this regional scale is that the plasma itself is a key participant in energy transport across the entire cluster volume. The plasma behaves like a heat reservoir that can radiate energy away via X-ray emission, and energy injection from energetic sources must offset this cooling to maintain temperature. If the balance between cooling and heating changes, the entire thermodynamic state of the intracluster medium can change. This region of space is not empty black void. It contains gas that has mass, temperature, metallicity, and velocity structure. Metallicity is the proportion of elements heavier than hydrogen and helium, and it can be increased over long time scales by supernovae that enrich the plasma. Signatures of metallicity can be detected in the spectral features of X-ray emission. Heavy elements in the plasma trace the cumulative history of star formation in cluster galaxies that released enriched gas into the intracluster medium. Thus, the hot plasma contains information about the integrated past of the cluster. Shocks and turbulence can arise when galaxies move through this gas, or when energy is injected into it. Turbulence here is not turbulence in the everyday sense of swirling air, but rather motions of a hot plasma over large distances that can mix material and distribute metals. The pressure of the plasma combined with gravity of the total mass, including dark matter, establishes hydrostatic equilibrium in many parts of the cluster where force balance holds. Hydrostatic equilibrium is the state in which the inward pull of gravity is balanced by outward pressure from the hot plasma so that the gas distribution remains stable on long timescales. X-ray observations allow astronomers to approximate mass distribution in clusters by mapping how pressure changes with radius. The Phoenix cluster has been modelled using such methods, but there are uncertainties associated with assumptions about the exact state of equilibrium. At this scale, those uncertainties are mentioned only to emphasize that derived density and temperature maps of plasma are not perfectly direct. The intracluster medium extends through the entire volume of the cluster, and this is the environment from which future inward steps eventually descend into the context of the most luminous galaxy in this particular cluster. But that narrowing inward is reserved for later sections. The intracluster medium is an enormous reservoir of mass and energy that permeates the region between galaxies and gives rise to X-ray emission over very large distances. It is a slowly evolving but not static medium that is shaped by gravity thermal, physics, turbulence, cooling, and energy injection. This medium is part of what makes the Phoenix cluster notable in the wider survey of clusters because its cooling properties differ from many cluster cores studied to date. But in this regional frame, no galaxy is singled out by name or by properties, because the focus remains on the plasma itself as the second layer inward from the full cluster scale, still covering many millions of light years and still free of details about any individual galaxy. This is a collective environment dense in total mass, but very thin in local density, radiating X-ray light from gas, at temperatures in the tens of millions of degrees Celsius, filled with metals from previous stellar populations influenced by shocks and buoyant bubbles, and held in place by the deep gravitational potential of the cluster as a whole. Cooling flows at the cluster scale refer to the slow net inward movement of hot plasma, when radiative cooling in some regions proceeds faster than the energy replenishment from other processes, and this section remains strictly at that intermediate regional tier, in which gas in the intracluster medium begins to move inward toward regions of slightly deeper gravitational potential, but without yet entering the specific interior of any particular galaxy. Radiative cooling in this context is a physical loss of thermal energy, as the plasma emits light, especially in the X-ray part of the spectrum, and as energy leaves the gas it becomes cooler on long timescales. As cooling progresses, the gas pressure can decrease, and where gravity is stronger, the plasma can slowly move inward, because gravity becomes relatively more effective when the opposing pressure is reduced. This is not turbulence, and it is not a hydrodynamic storm. It is a very gradual change in density and position over cosmic timescales, where gas that loses thermal support begins to drift inward. In many clusters, this process has been observed to be either suppressed or balanced by other heating sources such as jets from central galaxies. But in the Phoenix cluster, the balance between cooling and heating appears to be unusually shifted toward cooling in some regions. This difference is an important physical fact, because it means that thermal energy is not distributed in the same way as it is in many other cluster environments. The cooling time in specific parts of the Phoenix cluster core region is shorter than in many well-studied systems. Shorter does not mean short in absolute terms, since even a relatively rapid cooling time in a cluster environment is still vastly longer than any human lifetime by an enormous factor. But in the language of cluster astrophysics, this difference matters because it affects how much gas can condense, how quickly metal-enriched plasma can accumulate in certain gravitational basins, and how much mass can potentially begin to move toward denser surroundings. None of these statements imply or require speculation, and the scientific literature on the Phoenix cluster notes this relative difference in cooling performance compared to many cluster cores. The important point here is that a cooling flow region can supply gas to inner layers of a cluster environment, and the present scale remains strictly focused on this plasma movement between cluster-wide volumes and intermediate regions near the central basin. Gas moving inward under cooling flow conditions remains hot compared to most astrophysical environments, but it sheds energy faster than it gains energy from heating sources, so its temperature profile changes as distance to the gravitational center decreases. The term gravitational center here refers not to a single point, but to the region where the shared gravitational potential of the cluster is deepest. In many clusters, the brightest cluster galaxy occupies this deep potential basin, but that specific galaxy is not yet the focus of analysis. Instead, the focus here is on the fact that if cooling continues and the gas condenses enough, the flow of material can gradually feed into regions where galaxies, and especially the most massive and luminous galaxy in the cluster, can reside. Cooling flows at the cluster core level have been studied for decades, and they represent an important piece of cluster thermodynamics because they reflect the competition between radiative losses and heating sources such as active galactic nuclei. The Phoenix cluster is notable because it displays signatures that some gas has cooled rapidly enough to support high star formation rates once that gas reaches the environment in which molecular clouds can form. But in this section, star formation is not introduced yet because star formation belongs to a narrower spatial scale environment. Instead, here this is only a conceptual statement that if enough material moves inward via cooling increased gas supply, to inner gravitational structures can occur. But that downstream effect is reserved for subsequent sections. The present regional layer is large, covering many millions of light years, and concerns only the physical process of cooling, altering the density and motions of the intracluster medium. It is important to note that cooling flow does not imply unimpeded collapse. It simply refers to a net inward mass flux when cooling is strong enough compared to heating. In some regions of the Phoenix cluster, cooling dominates, and this has been inferred from observed X-ray data. Gas cooling in this way can lead to multiphase structure. Multiphase means that different temperature and density components can coexist in the same broad region of the cluster gas. Some plasma remains at extremely high temperature, while some pockets of gas become cooler. The cooler pockets have less pressure support because pressure in a plasma depends on both density and temperature, and if temperature drops, pressure drops, if density does not rise enough to compensate. This can create localized flows. The flows are not fast jets or violent streams, but slow drifts. The direction is toward deeper gravitational potential, which is near the cluster center. If the cooling rates are strong enough, the flows can lead to substantial mass accumulation over time. In the Phoenix cluster, these processes have been modeled, and models seek to estimate how cooling flows can deliver mass inward. Model uncertainties exist because the assumptions about hydrostatic balance, metallicity distribution, and temperature gradients affect numerical outcomes. However, cooling flow as a general category of physical process is well established in cluster astrophysics. The Phoenix cluster simply represents an environment in which this process appears to be unusually strong. At the cluster scale, this matters because it changes the supply rate of baryonic matter that can eventually reach the next inward set of physical regions. But now the narrative remains on this regional layer. This is a transitional frame which represents the path from broad intracluster medium to narrower environmental domains. The physics here is not about any single galaxy, not about any single nuclear emission structure, and not about any one compact object. It is simply the thermodynamic fact that heat loss from plasma can change the radial distribution of mass in a cluster-sized gas reservoir. Cooling flows in the Phoenix cluster thus form the broad conveyor of baryonic material, and this conveyor is shaped by gravity radiative losses and the thermodynamic properties of the plasma. It is a slow process. It is an energy balance process. And it is a process that has measurable effects in X-ray maps. In this step of the inward path, the only focus is that the Phoenix cluster is a region where cooling flows appear strong, and that these flows govern how much gas can begin migrating toward the central gravitational environment where the next regional layer will be located. The brightest cluster galaxy is commonly the galaxy that resides at or near the deepest part of the shared gravitational well, and in the Phoenix cluster, this role is occupied by a galaxy often referred to as Phoenix A, yet at this regional layer the approach remains galaxy scale rather than nuclear scale, and no features of the black hole or any inner accretion structures are introduced because those will belong to narrower layers not yet reached. A brightest cluster galaxy is a galaxy that outshines most or all other galaxies in its cluster, typically by a large margin, and these systems tend to be extremely massive, elliptical galaxies with large stellar envelopes and extended light profiles. The light from these galaxies is dominated by stars, and the total stellar mass is typically on the order of many trillions of solar masses for the most massive examples. Phoenix A is one of these giant cluster core galaxies, and it is surrounded by the intracluster medium described in earlier sections. The scale is smaller than the full cluster, but still enormous, measured in many tens of thousands of light-years in diameter. This galaxy contains stars that formed in many different epochs, as well as interstellar gas and dust that can supply more star formation under certain conditions. Observations have shown that this galaxy has unusually high star formation rates, compared to many other brightest cluster galaxies in cool core clusters, and these rates have been inferred from various wavelengths including far ultraviolet and infrared data. High star formation rate means a high rate at which gas is forming new stars, but here that detail is still treated only on the galaxy scale, not the nuclear scale, and not yet tied to the internal engine deeper in the core. In this region, the approach is to describe the galaxy purely as an integrated luminous system that collects baryonic matter delivered by the cooling flow region described previously. Galaxy-scale gravity is less deep than the full cluster gravity, but deep enough to trap gas that has crossed the cooling basin that shapes the previous section. This gas can settle into the outer regions of the galaxy and become part of the galaxy-wide environment. A galaxy is a system of stars, gas dust and dark matter, and in a brightest cluster galaxy, the dark matter is usually distributed in a very large halo. The stellar component is concentrated toward the central region, but extends outward in a diffuse envelope. The intracluster medium can interact with the outer halo of the galaxy in weak drag interactions which can slowly affect gas that arrives from the cluster environment. Over long periods, some fraction of the cooling flow material becomes part of the galaxy reservoir. Phoenix A stands out because its inferred star formation rates are so high that they are notable among known galaxy cluster cores. Star formation occurs in regions where gas becomes cool enough to condense into molecular form, but the exact processes by which gas transitions from hot plasma to molecular clouds involve intermediate phases of cooling, and those phases are not explained here because each region must be taken in order. The galaxy scale region is defined as the region where gas has already entered the gravitational scope of the galaxy and has become part of the interstellar medium. The interstellar medium includes warm ionized gas, neutral atomic gas dust, and potentially molecular clouds. Phoenix A appears to have substantial reservoirs of cooler gas compared to many other brightest cluster galaxies, and this is likely tied to the strong cooling flow discussed earlier. But the key discipline in this narrative is to keep this regional layer strictly at the integrated galaxy envelope level. The galaxy is the structure that receives matter from the cooling flow, and its interior is luminous in optical light because of the large number of stars. Some of the stars in Phoenix A are old, meaning they formed many billions of years ago, while some younger populations have formed more recently from the available gas. The mix of stellar ages in a giant elliptical system can be determined by analyzing the light from the galaxy across multiple wavelengths, and Phoenix A appears to contain recent star formation that is unusually intense for such galaxies. On the scale of this section, the galaxy is treated as a coherent gravitational object sitting at the center of the cluster, potential visible because of its stellar light, and because of the emission from gas that it contains, and because it intercepts inflowing mass from the cooling plasma environment. One may consider the galaxy to be the next inward reservoir into which baryonic matter flows. The movement from cluster-intracluster medium to galaxy-interstellar medium is mediated by gravity pressure gradients and radiative cooling. The morphology of Phoenix A is broadly elliptical, which means that it does not have a spiral disk structure, and its stars are distributed in a roughly spheroidal envelope. Elliptical galaxies are typically redder in color than spiral galaxies, because they usually contain older stars, but in Phoenix, a strong star formation introduces bluer components in some wavelength ranges, which is part of what helps identify that new stars are being formed. To remain in this regional scope, the focus must not yet shift to the very inner core of the galaxy. Instead, the emphasis remains on Phoenix A as a large stellar system with an unusually large gas supply, relative to many similar environments, where cooling may be less efficient. Phoenix A is a major recipient of the cooling plasma delivered from the cluster environment, and this galaxy represents the environment in which later inner processes occur. But because the formatting rules require strict avoidance of foreshadowing, the only permitted conceptual link at this stage is that the galaxy contains baryons, receives gas forms, stars, and occupies the cluster core where gravity is deepest. It is immense in stellar mass, immense in light, and immense in spatial size. Optical observations describe a large stellar envelope, while infrared observations describe heated dust from star-forming regions inside the galaxy. It is the dominant galaxy in this cluster, and it can be imaged as a smooth extended region whose brightness falls off gradually with radius. It is distinct from smaller satellite galaxies because of its size, brightness, and central position. This is the galaxy that defines the next inward layer in the path from cluster to core, but its nucleus and any nuclear activity are not the subject of this regional layer yet, because those belong to a narrower region. For the moment, Phoenix A is defined simply as the central brightest cluster galaxy in the Phoenix cluster, a massive elliptical system that receives gas from the cooling flow environment and contains both old stars and indications of significant recent star formation. The extreme star formation episode associated with this galaxy is an observational fact at the galaxy-wide scale, and this section keeps fully to that mid-scale region in which new stars are forming within Phoenix A, without yet describing any narrower nuclear structures or any inner compact source. Star formation is the conversion of cold molecular gas into new stars inside dense clouds, and in Phoenix A, the rate at which this happens has been inferred to be unusually high for a brightest cluster galaxy in a cooling core environment. These estimates come from measurements of ultraviolet light from young stars and infrared emission from warm dust grains that absorb ultraviolet light and re-emit at longer wavelengths. At this regional tier, those emission signatures are used simply to confirm that the amount of star-forming activity is very large. This galaxy-scale region is the location where large volumes of gas settle and where dense molecular clouds can form. The supply of gas that enters Phoenix A from the cooling flows described earlier can lead to reservoirs that are large enough to support rapid star formation. Although the cooling flows occur over extremely long time spans, the effect of sustained inflow is that the galaxy can accumulate baryonic matter faster than it would in a scenario where cooling is weaker. This leads to the existence of dense gas that becomes cold enough that molecules can form, and molecular clouds are the direct precursors to star formation. The overall star formation rate in Phoenix A is measured to be hundreds of solar masses per year across the galaxy, but because numbers must be described in words, it is noted here that hundreds means many hundreds of times the mass of the Sun turned into stars every year. On this scale, the exact mechanism of gravitational collapse of clouds is not necessary to describe in detail. It is enough to say that cold gas becomes gravitationally unstable when its pressure support cannot resist collapse, resulting in dense clumps that form new stars. The important fact here is that the galaxy displays star formation rates that are unusually high for a brightest cluster galaxy. This implies that a large reservoir of cold gas already exists within the interstellar medium of Phoenix A, and these star-forming regions emit radiation across a wide part of the spectrum. Observations at these wavelengths indicate regions of dust warmed by nascent stars, as well as emission lines from gas that has been ionized by intense ultraviolet radiation from newborn stars. Dust plays a critical role in galaxy-scale star-forming environments, because dust grains can absorb radiation and help gas cool. Dust also helps shield molecules from ultraviolet light that would otherwise break apart those molecules. Dust is made of complex compounds including silicates and carbon-based materials, and its abundance reflects the integrated past of star formation in the galaxy. Some of the dust in Phoenix A must come from older generations of stars that lived and died long before the present epoch observed. Some of it may form from new enrichment in recently dying stars, and some may have been transported inward with gas flows. On the galaxy-wide scale, this network of dust-gas radiation and gravitational compression constitutes a complex interstellar medium that has multiple temperature phases. But the main property being described here is the existence of strong and sustained star formation. A galaxy with high star formation rates must have a mechanism to supply gas to its inner regions. In Phoenix A, the unusual strength of cooling flows suggests that external gas supply is a major part of this process. But even as star formation proceeds rapidly in some parts of the galaxy, the reservoir must either be replenished or else star formation will decline when the gas is consumed. In the present section, the emphasis remains strictly on star formation as the main phenomenon of this regional layer. Star-forming galaxies emit light from young massive stars that live short lives and die as supernovae, and supernovae help inject energy and metals into the surrounding interstellar medium. This process creates feedback that can disrupt clouds, compress gas, and enrich the environment further. Some brightest cluster galaxies show moderate star formation, but Phoenix A is notable for its very high rates. The importance of this regional layer is that intense star formation represents a sign that large quantities of cold gas are present. Large amounts of cold gas in a galaxy residing at a cluster core represent a physical condition that has consequences for deeper interior environments. But because no foreshadowing is permitted, the only allowed statement here is that cold gas exists. New stars are forming at very high rates, and these facts are seen on the galaxy-wide scale. The source of this gas reservoir is the large-scale cooling flow that was already described, and the presence of this star-forming activity marks the transition from cooling flow zone to interstellar medium zone. It is critical to note that this is not an abstract interpretation. It is an observationally supported condition. The dust and gas content can be inferred from observations across multiple wavelengths, and these studies have shown that Phoenix A forms stars at a level that is many times higher than most brightest cluster galaxies. Without reference to narrower scales, high star formation rates indicate that the interior of the galaxy is not quiescent. The galaxy is producing new stellar populations. Some of the stars will be massive and hot and will live short lives. Some of the stars will be lower mass and live far longer, but all of them originate from cold gas clouds. The existence of so much cold gas inside this galaxy makes it a unique system at this stage of cosmic time, because this section confers the entire context of star formation. At this scale, it is sufficient to say that Phoenix A at this layer is a galaxy with a remarkable ability to convert cold gas into stars, and that the cold gas which fuels this process has origins in the larger cluster environment. The star formation rate is extremely high, the interstellar medium is rich in dust and molecules, and the galaxy-wide luminosity from young stars can be observed from great distances. All of these factors make the star-forming episode in Phoenix A a defining trait of this regional scale, and no narrower physical structure beyond this integrated galaxy scale is described here. The central region of the galaxy is the next narrower physical layer on the path from the broad star-forming envelope toward more compact inner environments, and in this section the focus remains entirely on the inner zones of Phoenix A, at the spatial scale still larger than any single nuclear compact structure, which means that the region described here is the extended central part of the galaxy, where stellar density is high, dust lanes can be thick and cold, gas can accumulate in concentrations that differ qualitatively from the broader interstellar medium of the galaxy at large radii. Brightest cluster galaxies often have extended brightness profiles that taper gradually outward, but toward the central region the brightness steepens and the stellar density increases dramatically. This central stellar concentration produces a gravitational basin that is deeper than the outer galaxy, and that can influence the distribution of gas dust and newly formed stars at these smaller radii. The presence of very high star formation rates at galaxy-wide scale implies that some of the cold gas must be distributed in this central region, because this is where pressure, gravity, and density conditions more easily produce the molecular clouds that collapse to form new stars. But the present section does not yet describe any accretion disk or any compact object, or any small-scale emission structure. Instead, the focus is the broader sub-kiloparsec domain, in which stars are densely packed, and where gas can exist in multiple thermodynamic phases. Cold, dense molecular gas, at this scale, can form filaments or clumps, and some observations of brightest cluster galaxies indicate that narrow filaments of cold gas can extend tens of thousands of light-years toward the galaxy center. These filaments, where present, represent channels of denser material that can fall inward under gravity. In some such systems, dust lanes have been imaged as dark bands against the bright stellar background, and these dust lanes trace the locations of cold, dense matter at this intermediate spatial scale. In Phoenix, a multi-wavelength observations have revealed that large masses of gas exist within the central tens of thousands of light-years, and that the concentration of cold gas here is particularly pronounced. The presence of so much cold gas implies that these central zones are not in a quiescent elliptical state as seen in many low-star-forming cluster core galaxies. Instead, the energy balance in this region is such that cold molecular gas can persist. The ultraviolet light from young massive stars in this region also heats dust, which irradiates in the infrared, and this infrared emission is observed from Earth as a tracer of ongoing star formation in the central region of the galaxy. An important fact at this stage is that the central region is not a uniform sphere. The density, temperature, ionization state, metallicity, and dust mass distribution vary with radius. But in this section, those variations are treated at a qualitative level. The central region can include warm ionized gas, neutral atomic gas, cold molecular gas, and dust, and these components interact with radiation fields from stars and from other processes. The radiation from young stars can create ionized zones in which ultraviolet photons strip electrons from atoms. These ionized regions can be observed through emission lines at specific wavelengths. In many brightest cluster galaxies with strong star formation, the central environment includes luminous emission line nebulae that trace gas densities and metallicities. In some regions, shocks can occur when gas clouds collide, or when stellar winds from young stars push through lower density zones. But the velocities involved at this intermediate region are lower than the velocities associated with relativistic jets discussed later, and are not the topic here. The purpose of this section is to identify that the central region of Phoenix A is dense, complex, and baryon-rich. The gravitational field here is stronger than in the outer galaxy, because more mass lies interior to any given radius. The deep gravitational environment can trap gas effectively. That trap can cause gas to settle toward the center rather than being dispersed outward. If gas accumulates, temperatures and density can evolve. The central region in Phoenix A is believed to contain a significant portion of the total cold gas reservoir of the galaxy. This fact is inferred from observations of molecular emission lines which originate in the densest cold gas. These molecular lines trace material at temperatures far below the millions of degrees Celsius found in the intra-cluster medium. Cold molecular gas can be at temperatures of tens of kelvins, which is close to the equilibrium temperature of dust in dense clouds, shielded from intense radiation. This wide difference in temperature from the surrounding cluster environment is one of the most striking markers of how deeply cooling processes have altered the baryonic state of matter in this galaxy core. But in this section, numbers are not emphasized because the uniform approach requires simple description rather than tabulated values. The central region is defined here as the region in which gas densities are highest, stellar densities are highest, and star formation is strongest. Radiation fields are intense, dust is abundant, heated dust grains emit infrared radiation that escapes to space. Ionized regions emit optical and ultraviolet radiation. All of these features coexist in the inner tens of thousands of light years. The baryon density here is so high that astrophysical models must account for multiphase structure. Multiphase in this context means that hot ionized gas, warm neutral gas, and cold molecular gas can exist simultaneously in overlapping spatial domains. This requires a combination of radiative heating, cooling shielding, and pressure balance processes. Cold molecular gas survives only if it is not exposed to enough ultraviolet radiation to break apart its molecules, and dust grains help shield molecules from such radiation. Observations of Phoenix A suggest that dust mass in the central region is high enough to support molecular gas survival. The star formation process here is intense and continuous. These intense star formation regions mark the transformation of baryons from gas into stars, but because this section must avoid foreshadowing, the only allowed conclusion is that the central region of the galaxy is a dynamic environment filled with cold, dense gas, significant dust content, ionized emission line gas, and high stellar density. This region is narrower than the full galaxy scale described in the previous section and broader than the inner nuclear region that will be described later. The central region is defined here strictly at this spatial scale, and its key characteristic is that it holds the highest concentration of star-forming material in the galaxy, likely because gas delivered inward from the larger cooling flow environment has become trapped in this deepening gravitational basin where the physical conditions support the continuation of very active star formation. Indirect nuclear signals are observational signatures from the central region of a galaxy that reveal the presence of a very powerful energy source in a much smaller inner domain, but do not directly measure its size or mass. And in this section, the focus remains strictly at that scale, in which nuclear-level energy output is detected through electromagnetic emission line excitation and compact high-energy features, without yet confining the description to a specific radius small enough to require explicit mention of an accretion configuration. These signals are called indirect because the physical object responsible for the power cannot be resolved directly at the required angular resolution, and the gravitational field at the very smallest radii cannot be measured through direct dynamical motions of individual clouds or stars in the way that nearby galaxies can sometimes be investigated. In Phoenix A, there are multiple lines of evidence that the central region hosts an active nuclear power source, because energy injection into the surrounding gas resulting in ionization, line excitation, and heating can be detected. In some cluster core galaxies, the nuclear region emits radio jets, and while this section does not yet introduce narrow collimated structures explicitly, it can describe the energy signatures that point to a compact engine. The most visible signs of an energetic central source at this scale include emission line regions that are too luminous to be powered by star formation alone, X-ray emission from hot ionized gas close to the center, and continuum radiation at optical ultraviolet or radio wavelengths that does not follow the spectrum of stars. Spectral line diagnostics at this scale can show ratios between emission lines of elements such as oxygen, nitrogen, and sulfur that are consistent with ionization by a hard radiation field stronger than stellar ultraviolet alone. When such line ratios deviate from pure star formation patterns, they are usually interpreted as evidence of a nuclear engine. The luminosity from this engine is not constant in time on cosmic scales, and in many cluster cores, nuclear activity can vary. But in any given snapshot of observation, the central region can show ionized filaments, shocked gas zones, and heating patterns that cannot be explained by starlight alone. These zones can exist at scales of many light years across, and because such structures are larger than the size of a compact nuclear object, they are considered indirect signs. They are not measurements of the compact object itself. They are the environmental consequences of an engine that injects energy into gas. In Phoenix A, the nuclear region has been studied at multiple wavelengths, and the evidence strongly suggests an active nucleus exists, meaning that material in the very inner region must be releasing large amounts of energy through physical processes not yet described in this section, because those processes belong to still narrower spatial scales. At the indirect nuclear signal scale, astronomers measure luminosity and spectral characteristics, and compare them to known templates of nuclear activity. Nuclear activity templates include broad and narrow line emission properties, continuum shapes, and variability. However, in Phoenix, a distance resolution and signal blending can make it difficult to isolate some of these components cleanly. Nevertheless, X-ray observations have shown energetic emission from the core region, and radio observations have shown central power output that is not attributable to star formation alone. In addition, large-scale structures in the intracluster medium can reflect nuclear energy injection, but those extended features are still not the main scope of this section, because those belong to a larger radius scale. Here the bounded region is the inner part of the galaxy where signs of ionization excitation and excess luminosity indicate a compact source. The reason this scale is so important is because direct dynamical mass measurements require resolving the motions of gas or stars very close to the central mass. In nearby galaxies like the Milky Way, this can be done at sub-parsec resolutions, but in Phoenix, the distance is so great that even the best telescopes cannot clearly track individual orbits near the compact object. Therefore, it is at this indirect evidence level that most information about the nuclear engine is derived. Observations reveal that the nuclear region is unusually powerful. The radiative energy inferred from these signals must come from a source that has access to gravitational potential energy at very small scales, or to mechanical energy provided by compact structures not directly resolved. In cooling core clusters, the interplay between nuclear energy injection and cluster gas. Cooling can lead to cycles in which the nucleus heats the gas, preventing cooling from proceeding too quickly. Yet in the Phoenix cluster, the cooling is still strong, so the balance between heating and cooling is unusual. Indirect indicators of a compact nuclear engine therefore must be understood in this context. The nuclear emission provides some heating, the gas radiates energy and cools, and the two processes form a thermodynamic relationship. In the central region of Phoenix A, the nuclear power source likely contributes to heating some of the gas, but not enough to halt the cooling flows entirely. The fact that cooling can still deliver large amounts of gas to the inner galaxy, and that star formation is very strong, means that indirect nuclear heating is present, but does not fully suppress cooling. The indirect nuclear signals detected in this region therefore represent one component of the energy balance. They provide evidence that a compact source is present. They also demonstrate that the radiation field is sufficiently strong that ionization at these radii is observable. The exact strength of that field can be constrained by emission line ratios and by modeling the ionization parameter, which describes the number of ionizing photons available per hydrogen atom. In this context, the nuclear radiation field is stronger than can be provided by star formation alone, because this section must not introduce any specific mass estimate for the compact engine. Yet the only allowed statement is that nuclear power is detected through indirect signals that fit patterns associated with active cores in other galaxies. The core region of Phoenix A emits ionizing radiation that illuminates gas clouds, causing emission lines that are not consistent with purely stellar ultraviolet sources. X-ray observations also show central emission. Radio emission also demonstrates non-stellar processes. All of these are indirect signatures of nuclear energy release. They imply a compact energy source. They do not measure its mass. They do not measure its radius. They do not confine its exact structure. They only confirm that there is a central nuclear engine active at this regional scale. Indirect mass inference theory applies when a compact central object cannot be weighed directly by tracking the orbits of stars or gas very close to it. And in Phoenix A, this is the case because the galaxy is so distant that spatial resolution at the scale needed for dynamical measurements of orbital speeds near the central region cannot be achieved with present instruments. In such situations, theorists rely on models that connect observed energetic output gas conditions and large-scale structures to plausible ranges of central masses that could produce the energy signatures seen. These models are not direct measurements. They are not the same as tracking stellar velocities in the way that has been done near the central mass of the Milky Way. Instead, these models estimate central mass by looking at the consequences a compact engine must produce in order to shape its environment at many thousands or many tens of thousands of light years from the core, and then inferring the gravitational potential required to power or allow such consequences. In the Phoenix cluster core where Phoenix A resides, some studies have proposed that the central compact mass could be extremely large, potentially on the order of 100 billion times the mass of the Sun. But because that number is not derived from direct dynamical measurement, it must be treated as a model-dependent estimate. The distance to this galaxy and the limitations of present telescopes mean that dynamical traces of the central gravitational field cannot be observed at the necessary resolution. The light from the nuclear region is also blended with other luminous features such as emission line gas and star-forming regions, which complicate spectral decomposition. The result is that mass inference is driven by indirect reasoning. One approach relies on comparing the scale of cavities in the hot intracluster medium to the energy required to inflate such cavities via nuclear activity. That approach involves estimating how much mechanical energy must have been injected into the surrounding gas. The size, volume, and buoyancy of those cavities then place constraints on nuclear power output. If that power output is persistent over some interval of time, it can be compared to theoretical models of accretion power. In accretion models, the energy released depends on the rate at which matter falls inward and on the efficiency of converting gravitational potential energy into radiation or mechanical energy. If the efficiency is known or assumed, estimates of the accretion rate can be made. From these accretion rate estimates, one can then infer the mass scale at which such power could plausibly be generated. But each of these steps contains assumptions. The efficiency of conversion from gravitational energy to radiation is not a single fixed number. The accretion rate is not directly measured. The cavity sizes have uncertainties. The history of nuclear activity may be episodic, with intermittent phases of high and low power. Therefore, the inferred central mass must be treated as a range of plausible values rather than a single confirmed figure. Another approach compares the total mass of stars in the galaxy to empirical scaling relations seen in other galaxies. Some studies have found correlations between stellar bulge mass and central mass across large samples of galaxies, but those correlations were derived from galaxies far closer to Earth, where the central mass could be measured dynamically. When applying these scaling relations to the most extreme brightest cluster galaxies, uncertainties grow because the most massive systems sit at the high end, where the validity of linear extrapolation remains untested. For Phoenix A, the stellar mass is extremely large, and if scaling relations held all the way out to such masses, one could expect a correspondingly enormous central mass. But because that conclusion would be an extrapolation, it must still be considered indirect. A third modelling approach uses the luminosity of the nucleus itself. If a certain fraction of mass energy is radiated as light during accretion, then the total luminosity can be used to derive the accretion rate. If the accretion rate is below certain stability thresholds, it may imply a central mass above a certain value to avoid exceeding radiative limits. But again, these estimates depend on assumptions about the radiative efficiency. In Phoenix, the nuclear region emits substantial radiation, but the exact breakdown of that radiation into stellar contributions, thermal plasma emission, non-thermal continuum, and compact nuclear emission introduces complexity. Separating each source of luminosity is necessary before such calculations can be meaningful. The indirect mass inference modelling process thus depends on the quality of data, the separation of emission components, the physical assumptions inserted into the equations, and the representativeness of scaling relations derived from very different galaxy types. When theorists propose that the central mass in Phoenix A could reach 100 billion solar masses, they are not claiming that this number has been observed directly. They are demonstrating that if the indirect signals are interpreted using standard physical assumptions, then a central mass on that order can plausibly power the observed environmental effects. Because a direct dynamical assessment is not available, the models cannot discriminate between all possible mass values. The underlying physical logic remains that energy observed in large-scale structures must have come from some mechanism, and compact engines powered by accretion are a known mechanism. If that engine is indeed connected to a massive central object, then that mass must lie in a range that matches the energy budget. In Phoenix A, the large cavity size is inferred from X-ray observations, and the extreme cooling flow conditions have pushed modelling results toward very high mass estimates. But caution is essential because these mass estimates have not been validated by dynamical tracers. As telescopes improve over future decades, higher angular resolution and more sensitive spectroscopy may make partial direct measurements possible for some distant brightest cluster galaxies, but at present Phoenix A remains out of reach for such techniques. The indirect mass inference approach thus remains theoretical scaffolding rather than measurement. It illustrates the potential scale of the central mass, but it cannot prove it. The purpose of this section is to define the physical logic behind that modelling approach, to identify that the estimates of enormous mass are not direct determinations, and to describe how scaling relations, cavity energetics, nuclear luminosity calculations, and accretion efficiency assumptions combine to create permissible mass ranges. This approach is standard in astrophysics when distance makes dynamical measurement impossible. In Phoenix A, this method has yielded possible mass values that are extremely large, but because all components of the inference chain have assumptions, the only scientific position that fits present data is that such mass figures are model-dependent and uncertain. They indicate plausibility rather than confirmation. The central mass could be very large. The indirect signals are strong enough to suggest that the mass is extreme, but indirect inference is not equivalent to direct measurement, and no direct dynamical mass for this system exists. Accretion structures must now be defined carefully, but still at a scale that remains more extended than the event horizon scale itself, because this section begins the introduction of the physical configuration that converts gravitational potential energy into radiation and mechanical output, yet keeps description at a radius large enough that the gas remains in a disk or torus-like configuration, rather than at any sub-horizon domain, which will only appear in later sections. Accretion means that gas loses angular momentum and falls inward, and because angular momentum prevents gas from going directly toward the center in a straight radial plunge, the material arranges itself into a disk-like structure in which differential rotation and friction-like processes transport angular momentum outward while mass flows inward. In galaxies with nuclear activity, this arrangement is called an accretion disk, though the structure can vary depending on accretion rate, magnetic field configuration, radiative efficiency, and gas supply. In Phoenix, indirect nuclear signals already discussed demonstrate that inward falling matter must release energy. That energy is usually interpreted as accretion power. Accretion disks are extremely hot in their inner regions because gravitational potential energy is converted into heat as gas moves closer to the compact object. However, in this section, the innermost heat-dominated zones are not introduced yet, because this must remain at the accretion structure scale overall, where the disk is large enough to interact with surrounding gas clouds, and to imprint rotational structure on emission lines. Observations of emission line broadening in some luminous nuclear regions in distant galaxies indicate rotational motion, but in Phoenix, the nuclear region is so far away and so complex in emission composition that emission lines are blended from star-forming regions, ionized gas clouds, and nuclear power. Even so, the presence of nuclear power implies that gas must be accreting onto something. Accretion theory describes how turbulent shocks and magnetic fields can redistribute angular momentum so that gas can move inward. Magnetic fields can tie gas parcels together and transmit angular momentum outward. Turbulent viscosity in disk theory is a parametrization of small-scale physical processes that allow this redistribution. As gas spirals inward, it heats up, glows, and radiates. In an active nucleus, the luminosity can be enormous. The disk is not uniform. Its temperature increases inward. Outer regions can be cooler and may contain dusty clumps or molecular gas. As radius decreases, the gas becomes too hot for dust to survive. Molecules break apart, atoms ionize, and the disk becomes hotter and more luminous. In Phoenix A, the accretion structure cannot be directly imaged, but the nuclear luminosity and energy budget imply that such a structure must exist. The accretion region is the zone where gravitational energy is converted into light, heat, and mechanical energy. Radiation pressure from the disk can influence the shape of surrounding gas clouds. Ionization cones can form when ultraviolet and X-ray radiation escape along paths of least optical depth, although the exact shape of such structures in Phoenix A is uncertain because of the resolution limits. Accretion disks are expected to have broad emission features in some galaxies where the line-of-sight velocity distribution is large. In Phoenix A, those broad components have not been isolated cleanly, not because they are absent, but because of the mixing of emission from star-forming regions and the limited resolution that blends signals. Still, the theoretical expectation is that an accretion structure exists. Accretion disks also serve as the launch region for mechanical outflows. Magnetohydrodynamic simulations show that jets can be launched from the inner region of the accretion flow when magnetic fields are twisted by rotation. Those jets inject energy into the surrounding medium. But the full description of jets belongs to a later section. Here, the description remains at the scale of the accretion flow as a reservoir of matter that is gradually moving inward. Accretion rate depends on the supply of gas. Because Phoenix A receives gas from cooling flows, and because its star formation rate is high, it is reasonable that the nuclear region has access to large amounts of cold gas that can approach the accretion structure. Observations of molecular gas filaments in cluster core galaxies show that cold gas can indeed reach the inner region. In some systems, these filaments appear to move inward along gravitational gradients. At this scale, the exact path of gas from the galaxy central region into the accretion region is not described in detail, but the fact that such filaments exist indicates that supply channels can operate. Once gas reaches the disk, it becomes part of the accretion flow. The physics of the disk depends partly on radiative cooling efficiency. If cooling is efficient, the disk can be thin, meaning that most of its structure is near the midplane. If cooling is inefficient, the disk can puff up and become thicker. The thickness of the accretion disk affects how radiation escapes and how outflows form. In Phoenix A, because the nuclear region is luminous, and because the large-scale environment shows evidence of mechanical power, injection, accretion must be present at a rate high enough to power the observed nuclear influence. But the indirect nature of the signals means that details of disk structure cannot be measured. The disk emits across many wavelengths. The hottest inner parts emit X-rays. The outer parts emit optical and ultraviolet light. Radio emission can arise from synchrotron radiation in jets or coronae, but again those features belong to narrower zones. Here the focus is that gas must arrange itself into a rotationally supported inflow structure that mediates the conversion of gravitational potential energy into radiation. Without accretion, there would be no nuclear power. Without nuclear power, there would be no indirect signals described earlier. Thus, at this scale, the accretion structure forms the physical transition between gas reservoir and the innermost compact region. This zone is not directly observable at high resolution in Phoenix A, but is mandatory in any physical interpretation of nuclear energy release. The existence of abundant cold gas in the central region means that the accretion structure likely has replenishment available over long timescales. That replenishment could support sustained accretion phases. But because this section must avoid previewing deeper scales, it only establishes that an accretion structure must exist, and that this structure is the region where gas begins to transform gravitational potential energy into output. Accretion theory is the key physics here. It is the mechanism that defines how gas moves inward past angular momentum barriers. In Phoenix A, this structure must be massive hot in its inner parts, cooler in its outer parts, and embedded in a dense environment rich in cold gas. But it is still larger than the smallest inner zone that will follow. The inner accretion environment is the region just inward of the general disk scale, but still outward of the smallest radii where gravity curves space-time enough that orbital velocities approach a significant fraction of the speed of light, and this section remains strictly on that transitional layer where temperature, density, radiation, field, strength and ionization reach levels vastly higher than in the broad disk zone, yet are not yet at the event horizon scale to be introduced later. In this inner environment, the gas becomes fully ionized because any remaining molecules or dust grains cannot survive the intense radiation field and high temperature. The material rotates at speeds that increase as radius decreases because gravitational force grows stronger nearer to the compact object. As the gas spirals inward, the potential energy drop becomes more extreme. The conversion of gravitational potential energy into thermal energy grows very efficient. The emitted radiation intensifies. At this layer, it's no longer sufficient to think of the gas as a cold inflow component. Instead, the gas is a hot plasma composed of ionized atoms and free electrons. Friction-like processes, better described as turbulent viscosity and magnetic stresses, convert orbital energy into thermal energy. That thermal energy radiates outward as electromagnetic radiation across a wide spectrum. X-ray emission, originating in this inner region, can reach very high luminosities. In Phoenix A, the nuclear region is too distant to resolve this inner zone directly, but the detection of hard X-ray emission from the core region suggests that matter is indeed reaching a domain where temperatures are extremely high. In accretion theory, this inner ionized region is often described as a flow in which cooling becomes less efficient as density decreases and as magnetic fields and turbulence dominate the energy budget. If the radiative efficiency is high, the plasma can cool by emitting light, and the accretion remains thin. If radiative efficiency is low, the inner flow can become geometrically thicker because heat is trapped rather than radiated away. These conditions depend on details such as magnetic field strength, accretion rate, and angular momentum transport mechanisms. Because Phoenix A is so far away, radiative diagnostics that cleanly determine which flow regime applies cannot be performed at the necessary spatial resolution. Instead, the observed output suggests that a hot inner flow is present because X-ray photons of extremely high energy are detected in the nuclear region. At this intermediate narrow environment, gas leaves the cooler outer disk. It moves inward through regions of increasing temperature until the ionization fraction is complete. The opacity of the plasma changes at these radii. Because atoms are fully stripped of electrons, emission and absorption lines become dominated by processes involving free electron scattering. The density of the plasma can drop toward inner radii, but the temperature rises sharply. In such conditions, the gas may become optically thin in some frequency ranges. Optically thin means that radiation can escape without being absorbed repeatedly. Optically thin flows can have very different spectral signatures compared to optically thick flows. In some theoretical models of extremely high mass black hole accretion, this inner region could behave like a radiatively inefficient accretion flow, where much of the thermal energy does not escape outward, but instead moves inward with the gas. That energy then becomes locked in the flow and contributes to pressure support. But in other models where radiative cooling is efficient, the flow becomes optically thick and emits more light. Because Phoenix's nuclear luminosity is large, and because cavity energetics imply high power, both regimes could be possible depending on accretion rate. This epistemic uncertainty must remain acknowledged because no direct spatially resolved spectral decomposition is available. Another feature of the inner accretion environment is that it can launch powerful mechanical outflows. At these radii, the magnetic fields anchoring in the inner disk can be twisted by rotation. That twisting can accelerate some plasma outward along the polar regions. Although the jets themselves belong to a slightly narrower level, to be addressed later, the physical cause for their existence can be introduced at this intermediate zone. The inner accretion environment is the birthplace of such mechanical outflows. Plasma in this region may undergo magnetic reconnection, turbulence, and relativistic acceleration. The existence of such processes in Phoenix A is inferred indirectly because large-scale cavities have been observed in the intracluster medium. Those cavities require mechanical energy input to inflate them. The inner accretion region is the only plausible source of such mechanical energy because star formation would not produce enough power. Therefore, the presence of inflated cavities in the large-scale cluster gas suggests that the inner accretion flow in Phoenix A must be capable of launching mechanical outflows. The radiation field produced by the inner accretion environment also affects the surrounding gas. Ionization cones or extended ionized zones can be powered by radiation leaking out from the inner region. These structures can extend far beyond the disk and enter the surrounding central region of the galaxy. At this radial scale, the shape of the flow is governed by gravity rotation, energy transport, and magnetic fields. General relativity begins to become important but not yet dominant compared to the region immediately above the event horizon. The energy extracted at this zone depends on the depth of the gravitational potential. For an extremely massive central object, the gravitational potential gradient is very steep. This means that gas falling from a radius even slightly larger to a radius slightly smaller can lose enormous gravitational energy in a short radial distance. That energy must go somewhere, and in this region it becomes radiation and mechanical energy. The geometry of the flow, whether thin or thick, depends on the accretion rate and radiative efficiency. Because Phoenix A likely has a large supply of gas, the inner accretion environment could sustain high accretion rates. That would lead to high radiation output and possibly thick disk geometries. It's even possible for radiation pressure to become dynamically important, pushing gas outward or inhibiting accretion in some directions. This dynamic interplay between inward gravity and outward radiation pressure defines the physical character of the inner accretion environment. In Phoenix A, this region remains unresolved, but model assumptions used to produce indirect mass estimates require that such an environment exists and that it is energetic enough to produce the observed nuclear signatures. All these physical processes occur in the inner accretion environment, yet the exact geometry, exact temperature profiles, and exact density distributions remain unknown due to observational limitations. Still, the physical principles are well anchored in accretion theory. The inner accretion environment thus represents a spatial scale just above the most extreme central region, and it is where gas becomes extremely hot, fully ionized, and highly luminous before descending further inward toward radii where orbital velocities approach relativistic speeds and gravitational fields become dominated by the compact mass at the center. Large-scale cavities in the cluster gas represent one category of extended structures that can form when mechanical or radiative power from the inner accretion environment is injected into the surrounding medium. But in this section, the focus remains entirely on these cavities as physical consequences at radii, much larger than the inner accretion zone and still narrower than the full cluster environment described earlier, because the spatial domain here is the mesoscale region, in which the nuclear power source influences gas, tens of thousands or hundreds of thousands of light-years away from the compact engine. Cavities are large, low-density bubbles in the intracluster medium, and they are detected through images that show depressions in X-ray surface brightness, because the cavity interior contains less hot plasma than the surrounding regions. Such depressions can appear as elongated voids or roughly spherical voids, and their morphology depends on how they were inflated. When energy from the nuclear region pushes outward through the hot intracluster medium, the mechanical work done on the gas can form buoyant bubbles that rise through the cluster atmosphere. These bubbles then displace plasma, creating cavities. In the Phoenix cluster, cavities has been interpreted as signatures of mechanical power injection that must have originated in the nuclear region of Phoenix A. These cavity structures exist far outside the central accretion region because they reflect accumulated mechanical work over long timescales. Their sizes are enormous. They can extend over distances that dwarf any internal accretion structure by many orders of magnitude. The amount of energy required to inflate these cavities can be estimated from the volume of the cavity, the pressure of the surrounding plasma, and the amount of work required to displace that plasma. When those energy estimates are derived, they imply that extremely powerful energy injection took place. This is one of the indirect lines of reasoning used to infer the existence of an extremely energetic nuclear engine. Cavity energetics depend on assumptions about how old the cavities are and on how quickly they rose through the surrounding environment. Buoyant rise times can be estimated by considering the density contrast between the cavity interior and the surrounding hot plasma. Lower density material rises through higher density material under gravity. The rise speed depends on drag forces and on the shape of the cavity. Therefore, cavity ages can be estimated by dividing cavity distance from the center by the expected rise speed. Multiplying the cavity power by the age gives an estimate of total energy injected. These energy estimates can then be compared to theoretical accretion power models to constrain the possible mass of the central engine. But direct measurements of cavity internal gas cannot be performed, so uncertainties remain. Nevertheless, cavity observations are among the strongest indirect indicators of extreme nuclear energy output. For Phoenix A, cavities in the intracluster medium appear larger and more energetic than those in many other cluster core systems. This means that the nuclear power source must have been especially energetic during the phases when those cavities were inflated. These phases may have been intermittent. In some models, nuclear activity can cycle between active and quiet periods. During active periods, mechanical outflows inflate cavities, while during quiet periods the outflows weaken. The cavities persist as fossil evidence of past activity. In Phoenix, a cavity sizes imply high power injection events. But this section does not examine the nuclear region itself nor the compact mass directly. Instead, the focus is on the cavities as physical outcomes of that power injection. The cavities are volume displacements in the intracluster medium. They are large enough to affect the cooling properties of the nearby plasma. Because the absence of hot gas in the cavity region means there is less material to radiate X-ray light. Therefore, cavities appear as darker regions in X-ray maps not because they are cold, but because they are thin in gas. Some cavities may fill with relativistic plasma from jets, others may be partially filled with turbulent gas, but the resolution is insufficient to measure cavity contents directly. The important fact here is that cavities prove that mechanical energy from the nucleus reached enormous distances. These distances lie between the inner accretion environment and the intracluster medium region described earlier. This mesoscale region is vast in its own right. The cavities can be oriented in pairs aligned roughly along the axis of outflows. In some cluster cores, cavities also show ripples or weak shocks. These shocks arise from pressure waves produced when nuclear activity varies. If energy injection increases suddenly, the pressure sends waves through the surrounding medium, compressing and heating gas. Shocks can be detected via slight temperature enhancements in the intracluster medium. In the Phoenix cluster, the combination of cavities, shocks and high cooling rates indicates a strong feedback cycle in which nuclear energy heats gas, cools, gas flows inward. Gas fuels accretion drives nuclear power inflates cavities, and cavities alter the distribution of gas in the cluster. But at this section, the description must remain strictly on the physics of cavities as structures that result from nuclear power at radii far beyond the inner accretion environment. The existence of such cavities tells us that nuclear energy is dynamically important at scales far beyond the precise radius where the central engine operates. Without such power, injection cavities would not reach such sizes. They mark the influence of the central engine on the cluster gas. Because the cavities displace gas, they can alter cooling times locally. Where cavities are present, there is less hot plasma to radiate. This physically affects the thermodynamic state of the medium. In some models, cavity rise can also stir the surrounding gas-inducing turbulence that can transport heat. In the Phoenix cluster, the combination of large cavities and high cooling rates suggests that nuclear heating is not fully balancing cooling. Some fraction of the gas still flows inward enough to fuel extreme star formation. This coexistence of powerful nuclear feedback and strong cooling flows is one of the most distinctive features of the Phoenix cluster. It means that mechanical energy injection was significant, but not destructive to the supply of cold gas. Therefore, cavities represent fossil evidence of powerful energy output, but do not imply full suppression of cooling. They only represent partial heating in the cluster core. This layer of analysis strictly isolates these cavity structures as large-scale environmental consequences of nuclear activity. They occupy a region that is narrower than the full cluster, but wider than the inner accretion environment. They are visible because they remove hot gas. They persist because they are buoyant. And they testify that the nuclear engine at the center of Phoenix A has exerted a profound influence over enormous spatial volumes. Jet-driven impacts refer to the mechanical influence that arises when narrow beams of accelerated plasma, originating from the inner accretion environment, propagate outward and transfer energy and momentum to gas at very large radii. And in this section, the description stays strictly at that spatial layer, where the jets have already left the extreme inner environment and are now interacting with the surrounding cluster medium, generating shocks, stirring turbulence, and sometimes carving channels that lead toward the cavities already described previously. Jets are thought to be produced when magnetic field lines threading the inner accretion flow or the region just above it become twisted by rotation, and these twisted magnetic fields accelerate particles along the polar direction, forming collimated flows that can remain coherent across very large distances. In the Phoenix cluster core environment, theoretical interpretation of cavity structure implies that such jets must have existed, because cavities that reach scales of tens of thousands or hundreds of thousands of light years, require sustained injection of mechanical power. The energy required to create such cavities cannot be supplied by stellar winds or supernova explosions in the central galaxy alone, because even rapid star formation does not create mechanical energy at the orders of magnitude required to shape the cluster gas. Therefore, jets are necessary in the physical interpretation of these cavity structures. The interaction of jets with the intracluster medium begins close to the galaxy center and then continues outward. When these jets encounter hotter or denser gas in the cluster core, they decelerate and scatter energy, which can generate shocks and drive turbulence. Shocks produce sudden changes in velocity, pressure, and temperature. These shocks can be traced in X-ray maps as waves or ripples. Turbulence can mix gas and distribute metals. If the jets are powerful enough, they can bore channels through the gas, and their endpoints can inflate cavities as the jet plasma pushes aside the intracluster medium. In this mesoscale domain, the jets are not described at the extremely narrow region of their launch, because that is a smaller scale that belongs to another section. Instead, what matters here is that jet-driven impacts create structures that extend across enormous radii. These structures are visible in cluster cores and are part of the broader feedback loop that couples nuclear energy output to cluster thermodynamics. In Phoenix A, the scale and significance of cavity structures imply that powerful jets must have existed, even if direct images showing jet collimation cannot isolate them clearly because of distance and blending of emissions. The fact that cavities are present means that jets propagated outward with enough momentum to carve through the intracluster medium. Radio observations of many cluster cores reveal lobes of relativistic plasma that are the remains of jet outflows. These lobes can persist long after the jet has weakened or changed direction. In some clusters, multiple generations of cavities and radio lobes exist, indicating that nuclear activity is episodic. If multiple cavity pairs exist in Phoenix A, this would imply that the nuclear engine has turned on and off several times over cosmic spans. Each outburst episode adds mechanical energy to the intracluster medium. But because this section cannot move outward into the full cluster environment, again it remains focused on the region where shocks, turbulence, and jet interactions actively occur, rather than describing how the entire cluster responds. Jets can also entrain gas, meaning that some of the surrounding plasma is dragged along with the jet flow. This entrainment can mix gas from different regions. If the jet encounters cold filaments, it can disturb them. In some systems, jets have been seen to interact with molecular gas clouds, compressing them, heating them, or pushing them aside. If jets compress clouds in a way that increases density, they can trigger star formation. If they heat clouds, they may temporarily suppress cloud collapse. These effects are not uniform. They depend on geometry, jet power, gas density, and pressure. Therefore, the impact of jets is complex. In the Phoenix cluster core, the fact that star formation remains extremely strong, while mechanical feedback remains extremely powerful, indicates that jet-driven heating has not been sufficient to eliminate cold gas inflow. Jets, therefore, provide heating but not disruption, at a level that destroys the ability of gas to cool. In some environments, jet impacts can create filaments of ionized gas that extend radially outward. In some cluster cores, long emission line filaments align with outflow axes. These filaments can be excited by radiation leaking through low-density channels carved by the jets. If radiation escapes along polar axes cleared by jets, then ionization cones can form. Ionization cones are regions of gas illuminated by intense radiation escaping the inner regions. In Phoenix, such structures may exist, although strong direct visual confirmation remains limited by distance and resolution. Jet-driven impacts can also redistribute metals. When jets stir gas, they mix enriched material from the central region outward. This mixing can flatten metallicity gradients in the cluster core. But because metallicity mapping in Phoenix A at high resolution is challenging, the exact degree of mixing remains uncertain. Nevertheless, the physical expectation is that jets are able to transport enriched gas outward at least partially. If the jets operate at high power, they can even generate weak shocks. Weak shocks are pressure waves that travel through the intracluster medium. They heat gas by compressing it slightly. The heating from weak shocks is distributed over large distances, and while modest in magnitude compared to the radiant energy lost through cooling, these shocks can contribute to maintaining gas temperature. But in Phoenix A, the cooling rate is so strong that these shock heating contributions do not remove the need for large-scale cooling flows. Instead, they demonstrate that mechanical feedback is present. Thus in Phoenix, jets create cavities, stir gas, generate shocks, and affect ionization and metal mixing. They are the primary channels through which the nuclear engine couples to the larger cluster core environment. But because this section must remain in the mesoscale domain, it does not describe the inner launch region, and does not describe the precise radius of the compact engine. It only describes what the jets do once they have left those regions. Here jets are defined as extended coherent outflows that interact with gas at radii far larger than the accretion scale. Their impact is seen in cavities, shocks, turbulence, and metal redistribution. Their existence is inferred from these consequences because the direct collimated structure cannot be spatially resolved. The scientific interpretation is that extremely energetic mechanical feedback from Phoenix A created these structures. Therefore, jet-driven impacts are the observable expression of nuclear power at enormous distances. They represent the physical link between the inner accretion environment and the intracluster medium. They show that the nuclear engine is active at a scale far larger than its immediate radius, and they demonstrate that mechanical energy injection from the core is an essential part of the energy balance in the Phoenix cluster core. The limits of current measurement define the observational boundary conditions under which all inference about the central mass in Phoenix A must be interpreted, and this section remains strictly focused on those measurement limitations as a physical reality of present instrumentation methodology, distance signal contamination, spectral degeneracy, and angular resolution, without introducing any narrower scale description of the compact object itself, because that belongs to a smaller radius yet to come. The Phoenix cluster is so distant that even the most advanced telescopes cannot resolve the inner few light years of the nuclear region with the spatial clarity needed to directly measure orbital velocities of stars or gas around the central mass. Direct dynamical measurement of a compact nuclear mass requires that individual traces can be tracked in motion, or line widths of gas can be decomposed at radii close enough that the gravitational potential becomes dominated by the central object. In nearby galaxies such as the Milky Way, such dynamical measurements have been performed by tracking individual star motions near the central gravitational source. But Phoenix A lies billions of light-years away. At such extreme distances, one cannot resolve individual stars in the central parsec. Instead, all the light from the nuclear region blends into one unresolved source. Spectral lines become blended. Component separation becomes extremely challenging. Moreover, the nuclear region of Phoenix A is embedded in an environment with intense star formation, and that adds further contamination, because emission lines from H2 regions associated with star formation mix with emission from gas ionized by the nuclear engine. Even if emission line widths could be measured from the blended spectrum, separation of rotational broadening from turbulent broadening or shock broadening becomes non-trivial. This signal blending is one reason why direct dynamical masses cannot be measured. Another limitation is instrumental sensitivity. High-resolution spectroscopy at such distances can detect only the brightest features. Faint continuum structure or faint forbidden lines that might encode velocity information are not detected at high signal-to-noise ratios. Without high signal-to-noise velocity, dispersions cannot be measured precisely. Even when high signal-to-noise is achieved, absorption line measurements from the stellar component would require spatially resolved spectroscopy to isolate the region close to the nucleus, and that is not achievable with current instrumentation. Adaptive optics techniques help for nearby galaxies, but the distance to Phoenix A prevents adaptive optics from increasing angular resolution, enough to resolve nuclear kinematics at sub-parsec scale. The fundamental angular resolution limit of existing optical and near-infrared telescopes prevents direct probing of the gravitational sphere of influence of the central object. The gravitational sphere of influence is the region where gravity from the central mass dominates over the surrounding mass distribution. That radius is small even for very massive objects. At the distance of Phoenix A, that radius subtends an angular size far below the diffraction limit of present instruments. Therefore, even if the central mass were enormous, the actual radius within which it dominates gravitationally would remain unresolvable. Another limitation arises from line-of-sight contamination. Dust lanes, cold molecular gas and star formation all contribute to attenuation and emission that modify the observed spectra. Dust extinction can suppress ultraviolet and optical emission. Molecular gas can emit in sub-millimeter wavelengths that overlay continuum emission. Emission line nebulae can have line ratios inconsistent with pure photoionization from the nucleus, because they can be affected by shocks or by young stars. These overlapping effects produce degeneracies in model fits. When multiple physical processes contribute to the same spectral features, it becomes impossible to isolate the nuclear gravitational signature cleanly. A further constraint is time domain coverage. Nuclear activity may vary, but repeated long exposure observations of Phoenix A at high spectral resolution are difficult because of observational scheduling constraints and the limited availability of the most powerful telescopes for long integration time at the necessary wavelength coverage. Without repeated observations, variability studies cannot constrain the central engine's short timescale behavior. Such variability is one of the tools used in nearer quasars to constrain size scales and mass. But in Phoenix, a variability analysis is limited. Another limitation arises from the need to subtract star formation contamination. In Phoenix, a star formation is so intense that the ultraviolet and infrared emission from young stars dominates in many bands. That emission shrouds the true nuclear continuum. If the intrinsic nuclear spectrum could be isolated, one could attempt to apply empirical scaling relations derived from quasar luminosity to mass relationships. But the nuclear spectrum is strongly contaminated by stellar and nebular emission. This leaves no clean path to extract the nuclear continuum. Because no direct continuum isolation is possible, mass inference must rely on mechanical energetics, such as cavity power or scaling relations based on total galaxy mass. But as described in earlier sections, scaling relations become uncertain at the high mass end. Thus, each inference path remains blocked by observational limitations. X-ray observations reveal strong nuclear emission, but the spectral shape at the highest energies does not contain enough information to resolve the innermost temperature profile. That prevents modeling of the inner flow regime. Radio observations show evidence of central power, but the radio emission is dominated by lobes and extended structures rather than by the immediate jet base. Without access to the jet base, the magnetic field strength and the initial outflow speed cannot be measured. Because these parameters are unknown, no precise connection between jet power and central mass can be established. Optical emission line kinematics in the nuclear region are also not resolvable at the required spatial scale. Even if broad components existed, they would be washed out by blending from narrow emission at larger radii. In summary, the central mass in Phoenix A exists in a region that cannot be spatially resolved with present telescopes. Signal blending prevents extraction of dynamical traces. Stellar and nebula contamination obscure the intrinsic nuclear spectrum. Multi-wavelength degeneracies prevent clean identification of nuclear emission components. Scaling relations become uncertain at the extreme high mass end. Cavity energetics provide only indirect constraints that depend on assumed accretion efficiency and duty cycles. All of these limitations mean that direct dynamical weighing of the nuclear mass is not possible today. The only scientifically responsible position is to acknowledge that current measurement limits prevent confirmation of the central mass, regardless of how large indirect inference models suggest it may be. Model sensitivity refers to the degree to which inferred mass values depend on the assumptions inserted into indirect inference equations, and in this section, the description stays strictly on the theory layer, in which numerical estimates of the central mass of Phoenix A are generated by parameter choices, efficiency, coefficients, duty cycle estimates, and scaling relation extrapolations, none of which are empirically measured at the radii that matter. Each model requires inputs, and each input is not known directly. Accretion efficiency is one example. The fraction of rest mass energy converted to radiation differs between radiatively efficient thin disk flows and radiatively inefficient hot flows. If a model assumes high radiative efficiency, then less material needs to be accreted to match observed luminosity. If a model assumes low radiative efficiency, then more material must be accreted. That difference alone can shift inferred mass by large factors. Another input is the duty cycle. Nuclear outbursts may not be steady. They might be episodic. If cavity power is derived assuming that the nucleus ran at roughly constant power for a long interval, then that model will produce one mass range. If cavity power is derived assuming that the nucleus fired in brief intense bursts with long, quiescent intervals between them, then the total energy required could be partitioned differently, producing a different mass inference. Because duty cycle history cannot be measured directly, modelers must assume a pattern. That assumption changes mass estimates. Another parameter is the accretion rate. If accretion is assumed to be near theoretical stability limits, then one set of mass values follow. If accretion is assumed to be far below those limits, then another set of mass values follow. Observational noise then interacts with these assumptions because portions of the nuclear spectrum remain blended with star formation. If ultraviolet continuum in a model is misattributed between nuclear source and stellar source, the inferred accretion luminosity changes, which then changes the mass estimate. Even the pressure of the intracluster medium needed to calculate cavity work depends on the assumed temperature profile. If the temperature profile is incorrect by even a modest fraction, cavity pressure estimates change and power estimates shift. Because cavity energetics are a core constraint used in some papers, errors in cluster temperature maps propagate directly into the mass inference. Metallicity distribution inside the intracluster medium also affects energy conversion. Radiative losses in cooling flows depend on metal lines. Higher metallicity yields faster cooling. If a model assumes metallicity is uniform while in reality metallicity gradients exist, then cooling time and mass supply calculations will differ. Underestimated metallicity can produce underestimated cooling rates, which then understate the mass delivered to the inner environment, which then understates the possible accretion rate, which then understates the possible mass. Conversely, overestimated metallicity could inflate mass estimates. The scaling relations also contain uncertainties. For galaxies with much lower mass than Phoenix, empirical correlations show that bulge mass correlates with central mass. But as one extrapolates to highest mass brightest cluster galaxies, the possibility exists that the correlation saturates, or that the slope changes. If slope is steeper, the central mass could be enormous. If slope is shallower, the inferred mass could be much smaller. Because the Phoenix cluster environment is extreme, even by brightest cluster galaxy standards, no direct calibration exists at this high mass end. Therefore, any extrapolation must be considered uncertain. Jet power also influences model sensitivity. If jets are assumed to convert gravitational potential energy to mechanical energy with high efficiency, then lower mass could produce the observed cavities. If jets are assumed to convert gravitational potential energy to mechanical energy with lower efficiency, then only larger mass could produce them. Because jet conversion efficiency is not known, the mass inference changes. Even the assumed magnetic field structure in the jet base influences the model. If fields are assumed strong, then energy extraction could be efficient. If fields are assumed weak, then the same cavity structure might require greater mass. Because those magnetic field configurations cannot be measured in Phoenix, models must choose a configuration, and choices change results. The accretion flow regime also matters. If the inner zone is assumed to be radiatively efficient, then a certain accretion luminosity implies a certain mass. If the inner zone is assumed to be radiatively inefficient, then mass must be larger. Because radiative efficiency cannot be extracted from present Phoenix, a data model selection creates a divergence in inferred values. There is also sensitivity to assumed geometric thickness of the accretion flow. If the inner flow is assumed thin, then radiation escapes differently than if the inner flow is assumed thick. That affects spectral shapes. Because observed spectra are blended theoretical, spectral decomposition is speculative. The spectral decomposition must assign relative contributions of starlight shock-heated nebula gas nuclear continuum and diffuse X-ray components. If any one of those assignments is even slightly inaccurate, the nuclear luminosity estimate changes, and thus mass inference changes. Model sensitivity is thus the cumulative result of all these parameter choices. In Phoenix A, this sensitivity is extreme because the nuclear region is heavily blended, heavily obscured, and deeply embedded in star formation. The indirect mass inference methods were not designed originally for cluster cores with star formation this strong. They were built for systems where nuclear continuum stands out clearly. In Phoenix, a nuclear continuum does not stand out clearly. Therefore, sensitivity to assumptions magnifies. A small shift in duty cycle assumption can move mass estimates from tens of billions of solar masses to many tens of billions of solar masses. A small shift in radiative efficiency assumption can shift mass estimates by factors that are large on absolute scales. Therefore, any mass value proposed for Phoenix A must be given with full acknowledgement that the inference is the result of an assumption chain. It is not a measurement. It is not a direct observation. It is the output of a physical model sensitive to input parameters not empirically determined. At present, there is no way to constrain those parameters with high precision, because observational limits described in the previous section block direct measurement of necessary quantities. Consequently, the mass estimates for Phoenix A reflect sensitivity to choices in model architecture rather than measurement of observable gravitational dynamics. This means that even though 100 billion solar masses is compatible with some models, the inferred value remains hypothetical, and subject to revision should future telescopes resolve the nuclear region directly. Until instruments can measure velocity gradients at sub-parsec radii in Phoenix, a mass inference will remain sensitive to assumptions, and the scientific interpretation of those assumptions must remain explicit. The state of knowledge inward refers to what can be stated scientifically about the innermost compact region of Phoenix A, while remaining confined to the strict limits of empirical support and acknowledging that the radius at which gravitational curvature becomes dominant cannot be spatially resolved at present, and in this section, the radial domain has now reached the final inward layer of the allowed outer to inner progression, which is the region immediately surrounding the compact mass itself, but still not the interior of any event horizon, because event horizons are not observable surfaces and cannot be described from direct measurement in any system, and certainly not in a system as distant as this one. At this smallest resolvable conceptual layer, the only empirically defensible statements are that a compact massive object must exist at the center of Phoenix A in order to power the activity observed at larger radii, that this object must have an extremely deep gravitational potential. Well, that this gravitational well is capable of driving accretion, in which gas loses angular momentum and falls inward, and that this accretion process produces radiation, mechanical energy, and ionization signals that propagate outward to the scales described in earlier sections. The existence of this compact object is not in dispute among astrophysicists, because the indirect nuclear signatures, the cavity energetics, and the jet-driven impacts all require a mass concentration in the nucleus of the galaxy. What is in dispute is the magnitude of that mass. As described previously, the mass cannot be directly measured by dynamical tracers, because the gravitational sphere of influence subtends an angle far below the diffraction limit of present telescopes. Therefore, no star counts no velocity, dispersion measurements, and no proper motion mapping can be used to weigh the central mass. The only scientifically appropriate description is that a compact massive object exists, that its mass must be extremely high to power the energetics seen, that its mass has been estimated by indirect theoretical inference to possibly reach hundreds of billions of solar masses in some models, but that no direct measurement has confirmed such values. The most scientifically accurate language at this innermost scale acknowledges that this compact massive object sits at a radius so small that even the inner accretion environment cannot be resolved around it. The gravitational force at these radii is enormous. The curvature of spacetime is strong. Material passing through these regions would accelerate to velocities close to the speed of light, but without spatial resolution, such velocities cannot be observed in Phoenix A. The innermost domain is a theoretical locus at the bottom of the accretion flow, where gas becomes tightly bound. The depth of the potential well implies that orbital periods become very short. In other galaxies where such regions can be observed, orbital timescales on these radii can be measured in days or hours. In Phoenix A, these timescales cannot be measured directly, but the physics remains the same. Gas that reaches these radii releases energy efficiently. The flow becomes gravitationally dominated. In this innermost region, general relativity becomes the correct description of dynamics. Newtonian gravity becomes insufficient. The gravitational acceleration approaches the limit at which no light can escape from within a certain radius, which is called the event horizon. But because event horizons have no surface, cannot emit photons, and cannot be spatially resolved in this system, the narrative must stop at the exterior of that conceptual boundary. The innermost accessible scale is therefore defined as the region at which gas in principle could orbit before crossing the boundary beyond which photons cannot return. That radius depends on the mass of the compact object. The larger the mass, the larger the radius of this boundary. For a mass on the order of many billions or tens of billions or hundreds of billions of solar masses, the boundary radius would be much larger than the boundary radius of a supermassive object in a typical galaxy. But because the mass cannot be measured, the radius cannot be specified. Only ranges derived from theoretical models exist. The interior cannot be directly described, because no information can be obtained from within such a boundary. The outer to inner narrative terminates here at the conceptual surface, where orbital motion radiation, mechanical energy extraction, and accretion power all must become concentrated to generate the signals measured at larger scales. The physics at this innermost accessible boundary depends on the spin of the compact mass, the orientation of magnetic fields, the accretion rate at that moment, and the spectral energy distribution at energies high enough to sample the thermal conditions of the plasma. Those quantities cannot be isolated clearly in Phoenix A. Therefore, the only scientifically responsible description of the innermost region is that it is a domain in which general relativistic gravity dominates, that gas falling inward must cross a threshold at which orbital stability ceases, that objects falling inward cannot escape back out, and that energy extracted from the gravitational field at radii outside that threshold must be responsible for powering the features already described at larger radii. This inward endpoint of the layered description is not an endpoint of physical curiosity, but it is the endpoint of empirical access. It marks the limit of what observation and theory can combine to describe coherently for this object. It is a region defined by gravity, by theoretical inference, and by the absence of direct measurement. All observational signals come from regions outside of this zone. All inference about central mass remains theoretical. All pathways of energy to the cluster environment originate outside of this boundary. And because no observation reveals detail within this innermost region, the scientific description ends here at the edge of the domain beyond which information cannot return. The state of knowledge inward is therefore the state of acknowledgement that the compact massive object exists, that it must be extremely massive, that the mass is unconfirmed in magnitude, and that the internal region cannot be observed. It is the conceptual boundary consistent with the physics of extremely deep gravitational wells in distant galaxy cluster cores, and it represents the smallest region reachable in the permitted outer to inner traversal.